Hello students, this video is the 5th lesson in the 6th unit. That unit is about triangle proofs, and this lesson is about the 5th postulate. We learned about 4 postulates already, SSS, SAS, ASA, and AAS. The 5th one doesn't conform to that. It's actually referring to a special type of triangle called a right triangle. It's called the Hyp-Leg or hypotenuse leg postulate, sometimes abbreviated HL, and it's very useful when you're looking at two triangles that happen to be right triangles. We're going to be talking about how to use this in proofs, how to mark up diagrams, and how to spot when we're using Hyp-Leg and when we're not. First, let's take a look at the learning target. The target here is I can explain the concepts behind the HL method, that's the hypotenuse leg method, and then prove the triangles are congruent using the HL method. Really, we're going to be proving triangles during this lesson. In the do now, it asks what rigid motions were performed on ABC to map it onto XYZ. And remember, map it onto is vocabulary that we learned about during the unit on transformations. Of course, map onto means to perfectly overlap, right? All of the parts of one triangle overlaps the other triangle. So B would perfectly overlap Y, for example. And then it says to sketch the intermediate images, if any. Try this out, pause the video, and see if you can sketch this out in your notebook. Okay, I broke this up into two different transformations, two different rigid motions. The first transformation, the first rigid motion, is a rotation of 270 degrees counterclockwise around point C. Point C is that center of rotation. And you'll notice that it sort of looks like B just sort of folded down to create B prime. We're not saying that we're rotating it in that direction, however, because in every case that we talk about, in the base case, we talk about rotating counterclockwise. So we got to rotate it all the way around. Now, once we see that rotation of 270 degrees counterclockwise around point C, then we can see that an easy way to take this triangle and take it to this triangle is to use a reflection or a flip. And you can see if I took this red triangle and reflected it over this vertical line that I drew in, it would map onto triangle XYZ. All right, there is your answer. What rigid motions were performed? We know that a rotation and a reflection was performed. You could, of course, done it in a different order. You might have reflected it first and then rotated it. But we do know that there has to be a reflection somewhere along the line, and here's why. In the unit, we talked about transformations. The word orientation means the order in which you name a shape by its letters. For example, triangle ABC has this kind of orientation. I go from A to B to C. It looks like this is a clockwise orientation. I'm spinning around the shape in a clockwise orientation, the same way a clock would spin. However, with XYZ, I'm going from X to Y, and then from Y to Z. This is a different orientation. It is a counterclockwise orientation, spinning around the opposite way that a clock would spin. So if I change orientation, the only transformation, the only rigid motion that requires a change of orientation is reflection. So you know that there has to be a reflection going on somewhere here. That's just a review of what you learned about in the transformations unit. Anyway, let's take a look at the turn and talk. What method can we use to prove that ABC and XYZ are congruent to each other? I'm going to erase some of this other stuff so you can see it a little bit more clearly and justify your response. Remember, the methods that they're talking about here, these methods are going to be the postulates that we learned so far. Okay, if you remember, we learned about 4 different methods so far. These are all the postulates that we've learned about. Let's write in postulates there. And remember that each of these postulates require you to know a certain number of things, a certain number of structures or parts of two congruent triangles. For example, the SSS postulate requires you to know that all 3 sides of the triangles, or all 3 pairs of sides, I should say, are congruent to each other. I know that this side is congruent to this side, right, because it's got 1 hash mark. This side is congruent to this side, but I don't know anything about this 3rd side, or these 3rd pair of sides. So I can't use the SSS postulate, unfortunately. The next postulate we're going to test out is the SAS postulate. Remember, SAS stands for side, angle, side. Side, angle, side is 2 sides and the angle that is included. Remember, included means between. So if I look at this shape, I can see that I have a side here. That's side BC, and that's corresponding to side YZ, and those 2 are congruent. I also know that I have side AC, which corresponds to side XZ, and those 2 are corresponding, and they're also congruent. However, the angle that we're given, which is angle A and angle X respectively, is not the included angle. That's an angle that's not between the 2 sides. So I can't use the SAS postulate either because I don't have 2 sides and the included angle. So since we're not using SAS postulate, let's see if we have ASA postulate. Well, luckily for us, this one and this one are pretty easy to figure out because in ASA postulate and in AAS postulate, they both refer to having two pairs of congruent angles. However, all I know about this triangle's angles are that they have one right angle. I don't know anything about angle C or angle B. I don't know anything about angle Y and angle Z. They sort of look the same, but remember, looks aren't everything. We can't judge by looks, so we can't tell whether two angles are congruent. So we can't use ASA and we can't use AAS. So with the information that we have here, so far the answer to this question is what method can we use to prove that triangle ABC is congruent to triangle XYZ? The answer to the question is we don't have one yet. Well, luckily for you, there is a fifth option, and that's the option we're going to be talking about today. That's the HL method, which of course, as I said before, stands for hypotenuse leg. In order to talk about hypotenuse leg method, let's take a look at the anatomy of a right triangle. You can tell that this is a right triangle because I'm going to make the marking here that shows that it's a right angle, and then we're going to identify the different parts of this right triangle. First, we can say that this is the right angle, and we'll put a right angle marker there. In a right triangle, it's required that it has at least one, or exactly one I should say, right angle. Remember, if it's got two right angles, it can't be a triangle because that's already 180 degrees, and all three angles added together have to be 180 degrees. These other two sides here, these sides that are adjacent to the right angle, are called legs. And later on in the class, it'll be important to distinguish between the long leg and the short leg. So for now, I'm going to call them long leg, which is LL, and short leg, which is SL. Last but not least, this side here, as you can see, is across the triangle from the hypotenuse. It's across the triangle from the right angle. So it is, of course, called the hypotenuse, right? This longest side in a right triangle, which is across from the right angle, is called the hypotenuse. All right, so here's some helpful definitions of parts of a right triangle that I'll fill in on the right-hand side here. It would be a good idea for you to jot this down into your notes. Just draw the picture, label the different parts of the right triangle, and jot down the notes that I have here. Okay, here's some factoids to know about right triangles. I'll let you peruse these at your leisure. You can pause the video to try to write these down into your notes, but let me continue with the hypotenuse leg lesson. Hypotenuse leg postulate, the HL postulate. Just to be clear, you'll see it in many different ways. You might see it as HL or Hyp-Leg or hypotenuse leg. If the hypotenuse and one leg, doesn't matter which leg, of a right triangle are congruent to the hypotenuse and one leg of another right triangle, then the triangles are congruent. Here we have three different parts. We have the fact that it is a right triangle. That's important to know first. And we also know that these sides, which are the hypotenuses of the triangles, are congruent. And we also know that these sides, in this case the long leg, could be the short leg, of the two triangles are congruent. Then we know that the triangles themselves are congruent. Now, if we weren't using Hyp-Leg, how would we prove that these two triangles are congruent? Well, if we were to trace along the triangle, starting from this vertex, vertex F, we would come to first an angle, and then a side, and then another side. I'm sure you'll agree that there's no reason for me to spell out what we get from that, but again, we never use that as a postulate because it's a rude word that you wouldn't say in polite company. Same thing here. Starting from this vertex, we get an angle, and then a side, and then another side. That's not a valid method of proving two triangles are congruent. That's angle, side, side. So we aren't able to use that postulate because it's not a thing, but we are able to use hypotenuse leg because this is in fact a right triangle. This is an exception to that rule where you can't use, that fake postulate that I just named. Okay, let's take a look at the check for understanding number one. Just look at these pieces of information, these diagrams, and see whether you can use HL postulate to prove the two triangles are congruent. And there was one piece missing here that I had to put in. That P is a midpoint of OQ. Okay, try this out, pause the video, and then see if you get it right. All right, again, the question was whether you can use HL postulate to prove that the two triangles are congruent, and in this case, we can't. Well, one thing that we know is that it is a right triangle because it has a right angle, and this is a right triangle also because it has a right angle. However, Hyp-Leg or hypotenuse leg postulate requires us to know the hypotenuse and the leg of each triangle. We know both legs because since G is a midpoint of EI, that means that GE and GI are congruent. We don't know anything about the hypotenuses of these two triangles. So since we don't know the hypotenuses, we can't say that we can use HL postulate to prove that these two triangles are congruent. But there's another method we can use. Starting from any old vertex, starting from E, let's say, I go side, angle, side. Looks to me like I'm going to be using side angle side postulate here. So SAS postulate is possible here. SAS and SAS. All right, for letter B. First of all, we know that AC is perpendicular to BD, which means that AC and BD form right angles when they meet. There's the right angles in blue. And we also know one other thing about side AC. This is a shared side between the two triangles, which means this side is congruent to itself. Of course, you know that this X is representative of that famous property, the reflexive property. So now looking at the two triangles, I have a leg of this triangle, AC. I have a hypotenuse of both of the triangles, which is AB and AD, and I know that they're right angles, so I know that they must be right triangles. So I have the three things I need: right triangles, hypotenuses, and legs. So in this case, we can use hypotenuse-leg postulate. So we are able to use that HL postulate because of the information stated here. Now let's take a look at letter C. We don't have any given information, we just have the stuff that's here. And at first glance, we have one leg, one hypotenuse, the longest side, and we should say that we have HL postulate. However, there's one thing that we need for hypotenuse-leg postulate to be active, and that is right angles. You can see in this case, this triangle does not have a right angle. This is an obtuse angle. As soon as you know that a triangle is one obtuse angle, you know it cannot have a right angle in it. So we can say we cannot use HL postulate here. Fairly straightforward. If we don't have right triangles, we can say that they are not eligible for HL postulate. We might be able to use something else, but we can't use HL postulate. As a matter of fact, let's take a look. In this case, we have an angle, A, which is congruent to angle D, and then we have a side and another side. So we have two sides and the non-included angle. Looks like A and then two S's. So doesn't sound like something that I would like to use in my geometry proof. Moving on to the last one, if we know that P is a midpoint of OQ, is this eligible for hypotenuse-leg postulate? As it turns out, if I know that this side is congruent to this side, if I know that this side is congruent to this side, and I know that this angle is congruent to this angle, I know that I have a pair of hypotenuses, NP and PR. I also have a pair of legs, PQ and OP, and I have a right angle, which makes it a right triangle. Looks like this is a perfect candidate for HL postulate. All right, so here's the first piece of this lesson, identifying whether you can use HL postulate in the different triangles. Let's take a look at this guided practice. In this guided practice, there's part of a proof, but we haven't finished off the proof. You're going to finish it with us here. So you can see that there's some given information. PM is congruent to RJ, PT is perpendicular to TJ, RM is perpendicular to TJ, and M is the midpoint of TJ. If I know all these things, can we prove that triangle PTM is congruent to a triangle RMJ? Let's make sure that everything is labeled in the diagram. In this first part, we know that PM and RJ are congruent, and there were already hash marks here. I just outlined them a little bit. PT and TJ being perpendicular, RM and TJ being perpendicular means they meet at right angles, which means I just traced out the right angles that they had here already. And M is the midpoint of TJ, which means that M cuts TJ into two equal pieces, TM and MJ, both of which are congruent to each other. All right, so moving on to the statements and reasons, taking a look at statement number 1, which is M is the midpoint of TJ, the reason for that should be given, as it is one of the given statements here. M is the midpoint of TJ, it's given. Next, we're trying to figure out what to say based on the fact that there's a midpoint. Well, since there's a midpoint, we know that TM and MJ are going to be congruent to each other. There's that statement there. Next, PT and TJ are perpendicular, RM and TJ are perpendicular. Well, we know that from the givens, so I'm going to say given. Once I know that these two sets of lines are perpendicular to each other, I know that these angles must be right angles because perpendicular lines form right angles. That's the definition of perpendicular lines. So my next statement is going to be that this angle and this angle are right angles because of the definition of perpendicular lines. And once I know that these two triangles have right angles in them, I can say that these two triangles are in fact right triangles because a right triangle is a triangle with a right angle in it. Once I know that these are right triangles, I can say that since they're right triangles and they have a hypotenuse and a leg that are congruent to each other, then we can say that the two triangles are congruent to each other. The reason being hypotenuse-leg postulate. And of course, you can write HL postulate or hypotenuse leg. You could write the whole thing out, but I like to write out Hyp-Leg because that's how I learned it in my geometry class. All right, moving on up to the last problem that we're going to be doing together, the model problem. In this, I'm going to let you pause the video, try this one out, and then come back to see my method on how to get this one right. All right, first I underlined the givens, labeled the diagram, and then I wrote down the givens in my statements and reasons. There's one other thing that I can tell right away, and that's that AC is that shared side, so I'm going to refer to that as reflexive property. And I fixed a typo here. This should have said AD, not AC. Anyway, AC is congruent to AC because of that reflexive property, that X in the middle, it's congruent to itself. Now, what I need to do before I use hypotenuse leg is say that these two triangles are right triangles, which requires me to say that this and this, angle BCA and angle DCA, are right angles. So now I have my three components that I need in order to prove these two triangles are congruent using Hyp-Leg. I know that they're right triangles. I know that the legs are congruent, AC and AC. And I know that the hypotenuses are congruent, AB and AD. And I've labeled those here for your knowledge. All right, now my last step, my last statement is going to be that these two triangles are congruent to each other because of Hyp-Leg postulate. There we go, I'm done. I would go over the check for understanding with you, but unfortunately that is for class. So that means this is the end of the video, the end of the lesson on Hyp-Leg postulate. Good luck studying.